Okay, in this video, I would like to talk about vorticity and circulation in a fluid flow. This topic is one of those topics that connects itself to lift and on a airfoil or on any object, as well as understanding the kinematics of the flow. Let's start with a background. These are the content that I will go through. The background, I will talk about flow kinematics, vorticity, circulation, and Kota-Joukowski equation. Um, if it fits in one video, we keep it there. Otherwise, it will be two videos to make sure that it doesn't become too lengthy and then goes beyond, the usually 30, 40 minutes or 50, but if it goes beyond that, I will make it into videos. So in terms of the background, we have seen in many cases that, if you have a candle, for example, and the smoke swirl around behind the candle, if you have, say, a stream, shall we say here, or you have seen that maybe a wing of an airplane, the flow goes around and we see some vortices or swirl flow around, behind the wing. So in general, we see that the flow spins. There is some rotational motion in the many flow that we, for example, these two examples and many other examples that we may have experience daily, or I'm sure many of us have seen it, but maybe have not paid attention to it. So we can come back here and say, okay, for having a flow going in a curved path or showing some rotation or swirling, do we need always to have a curved streamline? Or if I take a channel, for example, and a uniform, still, if I put some objects in this channel, do I see any swirling, or the object just will just translate from one location to another? So in other words, is every curved streamline, which is defined the tangent to the material line or the flow line, is a rotating flow? We can call it rotating flow. Or is every straight line streamline uh, free from rotation? So these are the good questions that we can ask, and we would like to kind of elaborate on these and give a discussion that clarifies these things. But let's go very simple sketch here. Simplified, I would say. I would like to establish the concept before going into the complexity of the mathematics or even the fluid flow. Let's say that we have an object, say a line, a bar, for example. And if I move this side with VB and this side with VA, but VA, the velocity and at two ends are equal, therefore I get some translation. Very simple. obviously our object AB will move from one location to another based on the velocity that we have, for example. Now, if I come and take the same object, and then this time VB is larger than VA, obviously I will get some translation, but in addition to the translation, I will get some rotation because the side B will go faster or further than side A. But this is a rotation in addition to the translation. Now, if I come and put the VA and VB in line with the AB, then obviously I will get some stretch. The line AB will be stretched or contracted. So here again, let's say VB is larger than VA, and then I get stretched. Now, I may have another case that I will consider my element as a square, and then because of the rotation of, let's say, this side and this side, or shall we say that my element strain in this direction, then we get strained. Strain bend is the angle changes from 90 degrees. By angle, I mean this one. So there is some changes in the angle. Okay, so this is very rough, simplified sketch of where we are getting into, and identification of several categories of motion that a material line in the fluid like AB can experience. Okay, now let's move to kinematics. If you have watched my videos on plates and beams, I usually start with kinematics, which is the source of any motion, and then based on kinematics we can go to strain and stress and so on. Now, in a flow, we consider velocity in general, or velocity vector, instead of displacement. If you like, we can say that we consider rate of displacement is considered, which is if I call it u here, vector, or ui, this vector has three components, And let's consider a coordinate system here, right hand rule. And these are the components in x, y, and z. So u is a function of x, y, z, and t. Similar, v could be a function of x, y, z, and t. And also w could be a function of x, y, z, and t. Components of velocity vector. So velocity is basically replacing displacement in fluid compared to solids. That's the first thing that we have to uh, consider and identify when we are dealing with kinematics in a fluid. Okay, so having said that, let's come here and say, okay, if I go back to my simplified version, if I have my A and B, this point A will have a velocity, let's call it UA vector, and UB vector, which is defined here. So this is what we are referring to, or it as a vector. So they have three components in the three-dimensional space. Now we come here and consider in our coordinate system, and I draw it again here. Let's draw it here in a maybe bigger scale here. This is my x, this is my y, this is my z. And let's say take a general point P located at R. So R is the position vector for P, and another point Q, position vector close to point P, position vector R plus delta R. So these are just two position vector in a flow, and then at some point with reference to our coordinate system we identify 2 points. Now this each point can have a velocity, let's call it u vector p, and u vector q. Obviously from vector triangle this would be my delta r, because r plus delta r should be giving me the position for the q. And if I draw something, I don't want to crowd the picture here, but if I come and draw a parallel to my UQ, then this vector would be my, maybe I move this, and then this vector would be my delta u vector. So back here, this is my up. But the green is not important, but the main point is that we are we are simply considering 2 points, one point here in the vicinity of that point with very small distance, point Q, and we identify the position vectors, and at each point we may have two different velocities up and okay. So there was a interruption, sorry about that, but we continue. Instead I wrote it down so we can go maybe faster. So we said that at point P we have velocity designated by UP, and at point Q in the vicinity of point P we have the UQ, the velocity for point Q. Now, why we are interested in these points in terms of their velocity? Because we are interested in relative velocity of two closely located points like P and Q. Because as I mentioned here, we are interested in the relative velocity in order to understand the kinematics of the flow. If every point moves with the same velocity, there is no rotation, there is no straining, it is just translation. So we would like to know the relative velocity. Now, it can be shown using a Taylor expansion. I will not go through it here, that this relative velocity that we are discussing here, and I designated here by delta u, in index notation is actually the gradient of the velocity vector times delta xj. Delta xj, I kind of use delta r at delta xj, the same. Uh, Maybe I also use delta r here, but since I use the gravity in the gradient, sorry, the gradient here, so I use delta x here as well. So x and r are kind of consistent here. I am considering x vector as r. It's not the x coordinates, it's the coordinates vector, position vector for any point that we are considering. Okay, so basically what we have here is the gradient of the velocity, which is a tensor, dot product with the with the vector position delta r. So this tensor or gradient of the velocity vector has a lot of information, and it is a second rank tensor, and when dot product with the delta r, it will give us a vector. For those of the you audience that are more interested to know about index notation and gradient of a vector, which is different from gradient of a scalar, uh, we can refer to my published book, Tensor Analysis for Engineers, third edition, 2023 published, or any other book on tensor analysis. But I extensively describe there with some examples about tensor notations and the gradient. I also mentioned that the gradient of the uh, a vector in different coordinates will have different form. So that's also extra information there. But here we are considering just a Cartesian coordinates for demonstrating this vorticity. Now, a lot of information in this quantity. So we come here and write it uh, in this format also. When you have index notation, a comma means differentiation. I and j can go 1, 2, 3. It can take the values of 1, 2, 3. So if I want this quantity, I will pick up half of it here and half of it here. and then add another quantity, which is the uj comma I, and subtract from it. So from in here, there's a trick here, but the beauty of this trick is that you will get a, this composition or these terms here. This is actually the strain tensor, and it is symmetric because if you exchange I and J, you get the same thing. This part is antisymmetric because if you exchange I and J, you get the negative of the value, so this is antisymmetric. Let's expand this part here. So if I come and take this part, which is the strain tensor, the diagonal, you get the du dx dy dv dy and dw dz, and again du u v w are the components of the velocity vector in our coordinate system. And for the second element, which is here exy, so you put 1 and 2, which is x and y, so you get derivative of u with respect to y plus derivative of v respect to x. And similarly for exz, and because this is symmetric, then you don't have to calculate all of them. You need to calculate the eyz, and that's it basically. Now for this one, this is antisymmetric. For a tensor which is antisymmetric, the diagonal should be 0, because in order to if you exchange I and J, it should be um, satisfy this relationship, and you cannot have a positive number equal to its negative value unless it is 0. And for the remaining terms, you basically calculate, and then you get the antisymmetric in there. So this is not symmetric, but this is symmetric. Now, this symmetric part, if you put it in a stress element, you see here that according to our coordinate system, this is Ex, Ey, Ez, normal strengths, and the in-plane shear and transverse shear strengths, according to the expressions that we have here. Now here is different. This brings some rotation, because see here that if I get du dy means the change in velocity in the direction of y, the change in velocity x in the direction of y, and the change in velocity v in the direction of x. So this indicates some rotation, but we keep it for now. And then we have this tensor, which we call it rotation tensor, or if you like, Cij. Now, let's form the curl of velocity any way that you want, either tensor formula, tensor or index notation formula is given here, or the traditional determinant way. So unit vectors along the coordinate system. The first vector is the gradient, and the second vector is the velocity. So you put the components and calculate the determinant. Now let's look at this one, for example. Let me maybe highlight this with green here, this term. If you go back to the elements of this antisymmetric C ij, you will see that you have this element here. Of course, divide by 2, but this is with the minus sign. Of course, it is here. Similarly, for this one, you see that you will get it here. And similarly for this one. So if I calculate the curl of velocity, which is the rotation connected to the rotation, I will get the part that I extracted from my ui comma j tensor, which is this part. Okay, so if I come here and call the elements of this uh, vector, which is the curl of u omega, and then I call the curl of u uh, 2 omega, therefore you can say this is 1 over 2 of omega, and then bring the 2 here. So omega is the angular velocity, and therefore you can say that omega, which I calculated here, is 2 times the vorticity. Okay, so this is actually the relationship between rotational and irrotational, or definition of rotational and irrotational. If you have irrotational, then your curl is 0. If you have rotational, the curl has a non-zero value, and then you can take it from there. So that is good enough for this video. We will continue with the next part, and then we look at maybe a quick example, and also the connection between the curl or the vorticity, which I defined it here, and the circulation.